I'm Holly Michael. I'm an assistant professor of hydrogeology at the University of Delaware. Everything that we consume requires water. So our water use is not just what we drink or what we use in the shower, but in fact our water use is much greater when we consider what we eat and the other things that we consume. We are starting to think a lot about how we use water and how that use affects both the quantity of water and its quality, and coming up with new ways of using water, using less of it, or using different types of water for different uses, I think is becoming very important, especially in water-stressed areas. Sustainability with respect to water quantity has to do with how much water is available and how much water we're using. And so we can't use more water than is in the system, and that's not sustainable. The ecosystems are highly dependent on the water, and so we have to think about using the water sustainably, not just for human consumption, but also for our environment. We want to use water in a way that we're not degrading the water quality over time, because when our sources become contaminated, they're no longer sustainable. Millions of people in southern Asia are drinking groundwater with dangerously high levels of arsenic. Almost everybody in the region is drinking groundwater, and mostly very shallow groundwater, which is where the arsenic is. So because you can't taste arsenic and you can't see it, then you don't know that it's there. And the health effects might occur 10 or 20 years later as cancers. So it's a difficult problem. This is our groundwater flow model of the Bengal Basin. The bottom is the bedrock, so that's the bottom of the model. In some places it's very deep. This is several miles deep, and in some places it's very shallow. In each of these little squares, the model will calculate the groundwater level, and based on all of those calculations, the model then calculates how the groundwater is flowing. We represent the geology, and we represent the hydrology that we can measure in the system, so how much rainfall, how much evapotranspiration, where the groundwater table is. We represent the land uses, so we know where there are agricultural fields and where there are cities and where people are pumping for human consumption and where they're pumping for irrigation for agriculture. We understand the physics of how groundwater flows, and we can represent that physics with mathematics. And with a computer, we can make lots and lots of mathematical calculations very easily. So we can represent this very complex three-dimensional system, and we can use that model to calculate how the groundwater is flowing. A model is never certain. A model is always our representation of a system, so it's never perfect, but we use them to understand how systems work. Besides our extraction of groundwater, then we have to also consider how the water gets into the system, which is the recharge. And that's primarily from precipitation. What's happening on the surface affects the groundwater flow because the groundwater and the surface water and the surface processes are all connected. Groundwater flows into the system through the surface. If there are pollutants on the surface, they go into the groundwater system. If the surface is not permeable, if it's paved, then the water can't flow in the system there, and that's going to affect the groundwater below it. And the surface water bodies also affect the groundwater because it's all connected. As climate changes, the hydrology of the systems change. So one aspect of climate change is temperature. So if temperature increases, evapotranspiration increases, that reduces the amount of water in the system. As climate changes, rainfall may increase in some places, it may decrease in others, and that changes the amount of water that goes into the system. Certainly, each system is going to have a different sustainable use of water. In arid systems, there's a lot less water available to both humans and to ecosystems. In humid climates, maybe there's a little more freedom. Always there's a problem with contamination. I work in estuaries in Delaware and in Massachusetts, and I also work on the beach on the Atlantic Ocean. In the coastal sites, one question has to do with transport of nutrients through groundwater into estuaries, and these nutrients come from agriculture. This can be a good thing, but it's also a harmful thing when there are too many nutrients. We think about sustainability of water supply in this area on the East Coast. We're fairly lucky here because it's a wet climate, so we don't have a lot of water availability issues, but water contamination issues could potentially be a problem. One way that we use our computer models is to try and ask questions about what may happen in the future, what might we expect. One of the reasons that I love being a geoscientist and I love studying groundwater is that it's interesting scientifically. I get to try and figure out the physics of these systems and how water flows, but also I think there's a big human component in it, and because we're talking about groundwater resources and contamination, it's important for us, for humans. I think it's exciting for us to have an opportunity to work on a problem that could hopefully help many people and could have potentially a very positive practical impact.